Hello.
Hey, Lina.
Hey, Anurag.
All right, we'll just wait one more minute and start.
Yeah. Should I start sharing my slides, or do you want to keep
Yeah,
the
maybe.
announcement?
Yeah, I'll make an announcement, and I'm sharing basically an announcement right now.
Yeah, that's good. Perfect. I'll just be waiting.
All right, so thanks everyone for joining, and today we have a pleasure of hearing from Dr. Lina Roald from University of Wisconsin Medicine, and she's going to talk about a very interesting topic, which is balancing wildfire risk and power system reliability with some preemptive power shuts off and proactive restoration planning. So Dr. Roll is an assistant professor and also a Granger Astute Fellow at the University of Wisconsin Medicine. She received her PhD in 2016 in electrical engineering from Zurich ETH, which most of us already know about. And before University of Wisconsin Medicine, she was a postdoc fellow with Center of Nonlinear Studies at Los Alamos National Lab. And her research interest is basically around modeling and optimization of energy systems with a specific focus on managing uncertainty and risk from renewable energy variability and component failures. With that, thanks so much, Lina, for doing for us. And with that, I'll stop sharing so you can share your screen.
Yeah, thank you so much for having me here. I appreciate being able to come here and give a presentation. Let me just try and share my screen here. Does that work? Are you seeing the presenter mode or the actual screen?
We see in presenter mode, yes.
You see the presenter mode, okay. How do I change this?
No, we see it in right mode. Yeah.
Oh, okay. You saw it correctly. Okay. Well, that's great. Okay. Great. Perfect. Yeah. Like I mean, I don't think I have any strange notes written down here, but you always want to share the full picture, right? Great. Okay. Yeah. So again, yeah, thanks everyone for coming here today and for having me here as part of this ESIC Power Group seminar. I'm excited to be here. And so as was mentioned, I'm going to talk about our work on balancing wildfire risk and power system reliability. And I'm going to talk about kind of two parts of this. One, which is about making decisions about public safety power shutoffs. And then I'm also going to talk about some algorithms that we're working on in order to enable faster restoration planning. Okay. And so, yeah, I'm sorry, there's some issue with my screen here. Okay. And yeah, so I also wanted to say that if anyone has any questions, meanwhile, while I'm talking, please feel free to interrupt, or I don't know how you normally do this, but definitely feel free to interrupt me if there's any clarification or any questions that you have as I'm going through this.
Yeah, normally put in the chat, so that can have a good flow, and then we, and also they don't miss their thought process, so they put in the chat, and I'll just put same thing again in the chat box.
Okay, well, that sounds great. Yeah, sure. Put it in the chat. If there's any urgent clarification, I should say, something you need to know in order to understand what I'm saying, then feel free to still, also write it in the chat or make me aware of something. Okay, so essentially I wanted to start out here with a slide that I'm assuming many of you have probably heard or seen before about resiliency of the grid. So this is a figure taken from Professor Strava's presentation at the PSARC webinar last November, which talks about resiliency as this process of anticipating, withstanding, and restoring after disturbances and large-scale things that can happen to the grid. So I wanted to also place my talk here kind of in the context of this question of resiliency, because you might have noticed on my first slide in my talk title, I talked about reliability. But also, this is, of course, very tightly, I mean, what I will talk about and how we are preparing ourselves for wildfire is also very much a question of grid resiliency. So in the first part of the talk, I'm going to really talk about how we can anticipate wildfire risk and try and optimize public safety power shutoffs to minimize this risk of wildfires, while also being able to serve as much load as possible in the grid. And then in the second part of the talk, I'm going to talk about our work on trying to develop scalable algorithms for power system restoration. So essentially, how do we decide on the order in which we are going to repair components that have been damaged? And so I also wanted to mention here sort of the way when I think about this in the terms of reliability, one way of sort of, if you think about reliability as sort of more the question of as an average over time, how much load are we able to serve to customers? What we are also doing when we are starting with public safety power shutoffs is that we are really reducing people's access to electricity during extreme weather. And although extreme weather is frequently not accounted for when we do count reliability of the grid today, I would argue that that is something we should start including in reliability metrics. So we are, when we're doing public safety power shutoffs in particular, we are actually, intentionally reducing reliability of the grid in order to address other types of risk. Okay, but yeah, so essentially part one, anticipating and preparing for wildfire risk, part two, restoring the system afterwards. Okay, so as I said, the first question that I'm going to talk about here is how to operate a power system in conditions with high wildfire risk. And this is what I'm presenting here is based on a recent paper with my student, Noah Rhodes, and our collaborator, Luis Ntaimo from Texas A&M, which is named Balancing Wildfire Risk and Power Outages to Optimize Power Shutoffs. So there's a link here that you can see in case you're interested in looking that up. Okay, so in the context of wildfires and power systems, we know that electric faults can cause sparks and arcing. So just, I'm sure many of you are aware of this, but just to kind of say, what is actually the process that is happening here. So essentially, if a power line is down due to wind or another external effect, then that power line can cause a lot of sparks and arcing. And also, if you have vegetation touching a line or anything else coming nearby a line, you can get these arcs that are very high temperature current flowing essentially through the air to ground, right? And of course, in this, both the sparks and the arcs release a lot of heat, which can cause ignitions, and that can lead to wildfires. So we know that there are several prominent wildfires that have been ignited by electric power grids. Maybe one of the most jarring examples in the US is the Camp Fire in California in 2018, which is one of the most expensive and also most deadly wildfires in United States modern history. There's also other fires in California that have been shown and proven to be started by electric power lines, such as the Kincaid Fire in 2019. This one is notable because it actually happened while the same area was under a public safety power shutoff. So despite having that public safety power shutoff, there was a line that was still in operation that actually started this fire. There are also a lot of other examples from other parts of the world. This is not just a California problem, it's also a Pacific Northwest problem, but also other parts of the world, such as Australia, which had their deadly, the Kilmore East fire, which was the deadliest of the Black Saturday fire in 2009. That was started by a power line and killed 159 people. So there's no lack, unfortunately, of these type of examples of wildfires ignited by electric power grids. So while we are seeing that there are these really large-scale fires that get ignited by power lines, there is also, unfortunately, so that ignition events in themselves are not uncommon. So PG&E itself has reported more than 400 ignition events just between 2015 and 2017. And in Texas, it is estimated that there's more than 1,000 fires that are being ignited by electric power lines every year. And so the other thing that we know is that wildfires that are ignited by power lines often tend to be large. And so over here, you see in this figure, this is a figure which shows statistics from wildfires in San Diego County. You can see this highlighted part here in red. That is the fires that are started by power lines. And if you look at this more closely, you will see that less than 5% of the fires that are started in this county come from power lines. But those fires actually account for more than 25% of the area burned. So why does this happen? Well, what happens is that it is more likely to get ignitions from power lines when we have high wind conditions. So because high wind leads to more movement of vegetation, it's more likely that the branch will float through the air and hit the power line and cause an ignition. So high wind leads to a higher probability of power line ignitions. And then once you have a fire that gets started, that fire can also spread faster and cover a larger area more quickly when we are having high wind conditions. So there is this unfortunate correlation between having a higher chance of ignitions and also having a higher probability of large fires. So that is also just to say that. Another thing that we know is that the wildfire risk is increasing. As we are seeing, as we're going to see climate change unfold, we know that there is going to be an increase in fire weather, more or less across the whole country. So what you see here on this figure is just a figure that shows the increasing number of days with high wildfire potential on public lands. And this is from a high emission scenario. But what you can see here is that essentially everywhere in the country, I mean, there is large areas here that are white because we're only looking on public lands, and there's more public land in the West, for example. But what you see here is that everywhere it's expected that the number of days with high wildfire potential is going to go up. And of course, that's not only going to be the case for public lands, but also in general. So this raises the question of how are we as power engineers and as for power system operators, how are we going to respond to these changes? And so what we have been working on here is first trying to model and to develop models of wildfire risk and ways in which we can address and try and mitigate wildfire risk. And there are some particular aspects of wildfire risk that make it a little bit different than other kinds of disturbances that happen to the power grid, because wildfires actually originate from the power lines themselves. Okay, but so let's talk about modeling and mitigating wildfire risk. So if we want to lay out what wildfire risk look like, we can think about it as the combination of essentially three things. So the wildfire risk can be expressed as the probability of seeing an ignition times the size and intensity of the resulting fire times the damage caused. So essentially, what was it that was burned by this fire? Of these three components, the utilities that are operating the power system are mostly controlling just one aspect. So mostly utilities can only control the probability that there will be an ignition from the power lines. They do not really have any jurisdiction over how the fire is fought once it has started, and they also don't control, what is just in that area around the power line. They are dealing with the power line and sort of the right of way around the power line. And so in order to implement risk reduction strategies, there are different ways the utilities are working on this. So you can do infrastructure upgrades. Could be undergrounding of lines, could be installing new equipment or new fault current interrupters, for example. You can do vegetation management. You could work towards having more frequent maintenance so that you're sure that your components are less likely to fail. But all of these three different kind of ways of trying to reduce risk are all long-term solutions. So these are solutions that will mitigate wildfire risk. They also have the benefit that they will improve reliability overall, because what we are trying to target here is the probability that we are going to see a fault. However, also all of these long-term solutions, they require investment and time for implementation. So if I'm standing today and I have to make a decision about how to operate the power system for tomorrow, I typically don't have time to do these kind of investments. Instead, when utilities are trying to mitigate wildfire risk in the short term, they have a much more limited set of solutions available. Such solutions involve, for example, disabling automatic reclosers to make sure that, if there is a fault, that we don't reclose on that same fault and get twice the fault current at the same location. Or the more disruptive version is to start public safety power shutoffs, where you actually intentionally take certain lines out of operation, you de-energize the lines so that there is no current flowing, which means that you have a zero probability of starting a fire, but you also don't get to actually send any power across that line. So you cannot serve the customers through that line. And so these are shorter term solutions. They are beneficial in that they mitigate wildfire risk, and they're also relatively fast to implement if you are able to control the settings of the automatic reclosers at a distance, and you can also switch off lines at a distance. The drawback here is that this will reduce reliability, or it will reduce the ability of the system to serve its customers. So it's reducing the amount of power that can be delivered to the loads. So just one example of this from October 2019. So this is one of the first large-scale public safety power shutoffs that happened about 1 year after the campfire. So PG&E started a public safety power shutoff, which shut off power to approximately 3 million people. So this was a huge, large-scale event, right? So now the question we can ask is, was that worth it? And when you go in and you look at their documents and their statements after these public safety power shutoffs, when they inspected the lines, they found that there were 100 potential wildfires that were avoided by shutting down those lines. And so now you can ask yourself, they took away power from 3 million people. Some of them lost power for days. But at the same time, they were able to avoid 100 potential wildfires, all of which could have become really large scale and really gone out of control because of very, very, very windy conditions. And so now the question becomes, how do you actually balance these two risks? It's really disruptive to lose power, but it's also terrible if your home gets burned down. And so overall, in trying to balance these two sources of risk, the main question that we have to try and answer is, which lines is it that actually should be turned off? And so if you look at how PG&E is doing this, we're just using PG&E as one example here. Other utilities also do this. They are looking at questions such as how likely is it that we're going to see outages? So you have a question of do we have, for example, outage producing winds, which is a main driver of the faults, as we have discussed before. And also, what is the risk of the fire that would be started if there was an ignition? And so you have these two different components that they combine, and essentially they come up with some kind of a risk threshold where they say that if a line has a too high risk, we are going to take it out of service. And so our question was, is it possible to do better? Because it seems like if you're only looking at the wildfire risk associated with individual lines, you are not explicitly taking into consideration what the resulting load shed would be if you turn off that line. So you could think of two lines having the same wildfire risk, one of them having a very big impact in terms of the amount of load that can be served, the other one having a much smaller impact. In that case, maybe you should be, turning off the one that doesn't have a big impact on the load shed, but you might want to keep the other one in operation. So that was the question that we were trying to answer here. And so that led us to formulating this problem, which we refer to as the optimal power shutoff problem. So in our optimal power shutoff problem, we have an objective function that has two terms. The first term here is saying that we want to maximize the amount of load that is possible to deliver to the customers. And d tot here, that is an optimization variable, which represents the sum of the weighted demand at each node. So essentially, D here is the demand at each node. W here represents a weight, so we can say there are certain critical loads that we want to prioritize over other loads. And then X here is a fraction of the load that is shed due to power shutoff. And I should say here we're considering this as at the transmission level, so that is why it might make sense to think of the load at different nodes in the transmission level as being sort of continuously sheddable. Then we have a second term in this objective function, which is looking at minimizing wildfire risk. So here, this R fire is again an optimization variable that is expressed as the sum of the risk of all energized components. So we have components here. We have a risk that is associated with delivering load. So this could be seen as the risk of wildfire ignitions in the distribution grid. We have a value which represents the risk of starting a fire from a generator, from a line or at a substation. And for these three last components here, you can see that we have binary variables that describe whether or not they are on or off. So if Z is set to 0, we are turning the component off, and we are also setting the risk to 0. If that component is turned on, then Z is going to be equal to 1, and then we have a non-zero risk associated with this component. So that is our objective function. There is also one thing that I haven't talked about here, and that is this parameter alpha. So alpha here is a parameter which determines the trade-off between the load delivery and wildfire risk mitigation, and how heavy we are weighting each of them. So you can see that if I set alpha close to 1, then I'm putting a very strong weight on this on reducing wildfire risk. Whereas if I set alpha close to 0, I'm putting a very high. I'm only focusing on delivering load, and I don't care as much about the fire risk. And so we can vary this trade-off parameter and solve the problem for different values of alpha. And that can help us understand, what is the full trade-off that we can get between wildfire risk and load, because these are two values that might not be so easy to directly compare. Okay, so given that objective function, we also have to model how the different things fit together. For example, in order to say something about how much load I have to shed if I shut down certain components, I also have to model the rest of the system. So we include constraints here that represents the relationship between different components, generator constraints and power flow constraints. And I'm just going to take you through this very quickly. So for our component interactions, we have that if a bus is disabled, all components that are connected to that bus are also going to be disabled. If a generator is disabled, its power output is set to 0. If it is not disabled, or if it is running, then we are enforcing standard generation limits. Then we also have, similarly for a line, that if it is disabled, the power flow is set to 0. And if it is not disabled, we are still also enforcing standard power transmission constraints. And you can see here that in this case, we are looking at the DC power flow representation of our power flows. And then we also have that the power balance must hold at each node. So this is just sort of a standard DC power flow, but where we are able to turn off some of the lines and also shed some of the load. And so putting it all together, we get this formulation here. We are trying to maximize load while minimizing wildfires. We are trying to increase. So we have this expression for the total load served, the other expression for wildfire risk. We have an expression for the power balance, power flow, generation, and the component relationships. So this is the type of optimization problem that we're trying to solve. I should also just mention here that this is a mixed integer linear program. All of the things that are marked in green here are integer variables, and all of the blue ones are continuous variables. So this just tells you that complexity-wise, this is a little complicated because we do have these integer variables that makes the problem a little harder to solve. But overall, because we're using a DC power flow, sort of the continuous part of the problem is pretty simple. Okay, so let's look at some results here. So going through a case study, I'm going to show you a little test case that we put together. So this is the IEEE RTS GMLC test case that has been developed by NREL. It is a very standard test case, which is essentially located in California. It has a lot of renewable energy, as it has been updated kind of recently to reflect a system with more renewable energy attached to it. And so and one of the things that is beneficial for us is that there are geolocations associated with each of the buses of this system. So we essentially took this system, as you can see here on the map. We placed it in California based on the placements that are provided with the system itself. So this is not something we invented. And then we put that on top of a wildfire risk map, which is similar to which is sort of representative of the wildfire risk seen in California in October 2019. And essentially here you can see on this map that this is the coast over here. This is the border to Arizona and Nevada. And you can see that there are certain areas that have a very low risk that are white. We have areas with medium risk, which is yellow, higher risk, darker yellow, and very high risk in orange. And so essentially for each of the lines and each of the loads and each of the buses and each of the generators, we are estimating the risk just based on their locations on this map. And then we are also making some adjustments for lines based on their voltage level, because we know that lower voltage lines are more likely to cause ignitions. So this is just how we put together this test case. So let's look at some results here. So in our original system, where everything is just working as normal, we have a total risk, which is 746. So there is no units associated with this number, because this is just essentially numbers that have been based on numbers that have been assigned for these different wildfire risk levels. And then we have a load served in the system, which is 8,550 megawatts. So then what we are going to do is that we're going to solve this problem for two different values of alpha, where alpha is representing, you know, the trade-off between load and wildfire risk. And so we're going to first start out and look at kind of a medium risk case, where we are actually going to give a pretty small weight to alpha. So in this medium risk case, where we set alpha to equal to 0.01, what we see is that we get this system solution over here. So you can see here that this is the same system. Some of the lines are still in green, meaning that they are still operating. We have nodes that are also still operating. All of the blue dots represent generators in operation, and then we have some gray dots that represent disabled generators. And then on certain of the buses here, you can see that this is there is red color. This means that the load has either been partially or totally shed on those nodes. And so what you can see here is that essentially in some parts of the system where we are close to this this dark red areas, we are shutting down more of the lines. And by shutting down those lines and shutting down many of the generators also in this area, we are able to reduce the total risk here by 57%. And that risk reduction comes at a very small decrease in the amount of load served. So we're only shedding 10 megawatts of load here. And I should also mention that solving this problem only takes us 0.3 seconds. So now you can ask what happens if we weigh the wildfire risk itself higher. So here's another solution over here where we have set alpha to 0.15. So now we are putting a much higher weight on minimizing the risk of the fire relative to the load. And so you can see in this case, we have reduced the total risk by 92%. But we are also reducing the amount of load that we are able to serve by 15%. But you can still see percentage-wise, we are still able to reduce the risk a lot more than we have to reduce the load. And again, it solves very fast. One thing to note here, because we have reduced the load by more, you can see that there's a lot more nodes here that have load that is shed, particularly in this area where there is a lot of wildfire risk, but also in certain other parts over here. So one thing that is also worthwhile to note in this solution is that you can also clearly see the benefits of distributed generation. There are multiple islands in the system where we can see that you have loads that are being served locally by local generation. And generally here you can see that there's a lot of different generators because there are many small renewable generators attached to the system. And you can clearly tell that that is helping improving the amount of load that is able to be served. So we're also not only interested in understanding how our method works, but we also want to understand how does it work relative to kind of what we consider to be more similar to the state of the art, where we are looking at more of a transmission risk threshold when deciding which lines to turn off. So if I look at risk threshold measures, then or the risk threshold here, that risk threshold is only measuring the wildfire risk. It does not take into account the resulting impact on electricity delivery. So that is something that is worthwhile to remember. We talked about this before. So what I'm going to do here is that I'm going to compare the wildfire risk level and the total load delivery that we are able to obtain with this kind of current practice wildfire risk threshold method versus our optimal optimization-based optimal power shutoff method. And so in this transmission risk threshold, we have one parameter, our Lmax here, which is helping us describe, what is our risk preference. Whereas in our optimal power shutoff, we are looking at this trade-off parameter alpha. So essentially what I'm going to do is that I'm going to, take these two methods and I'm going to evaluate the wildfire risk and load delivery for the different values of this Rmax and alpha values. And I'm going to plot the results here on this graph here. So you can see on the y-axis, we are seeing higher wildfire risk. On the x-axis, we're seeing higher load delivery. So where we really want to be on this graph is over here in the corner, where we have low wildfire risk and higher load delivery. So think about we want our methods to allow us to come as close down into this corner as possible. And so if I do this, I will solve this problem now for multiple different values of Rmax and alpha. And that will give me this Pareto optimal curve that tells us, what is the Pareto optimal front for different solutions that I can obtain here based on different risk preferences. And so here are the solutions. And so the optimized shutoff solutions are the ones here in blue. The ones that are based on just the risk threshold are the ones in yellow. And what we observe here is that for the optimized shutoffs, our solutions are all, you can see that all of the solutions for a comparable load level, the wildfire risk is always lower for the blue solution than the red solution, or for a given level of wildfire risk, we are always able to serve more load with our optimized shutoffs. So this is sort of looking at this trade-off. We can tell that our optimized shutoffs achieve lower risk and smaller outages sort of across the board for any different risk level. And so that also then raises the question, how is this possible? Did we just get lucky here, or why is this working? What is it that's going on? What's the mechanism by which this is happening? And so in order to understand that a little better, we will look at the wildfire risk and the power delivered in a little bit more detail. So essentially, you can think about, we have our solution here, and we are going to take all of our lines and we are going to insert them into this graph, where we are on the x-axis, we will look at the risk value associated with the line, and on the y-axis, we will look at the amount of power that is being sent across this line. And so we're actually going to do that first just for our threshold heuristic. And so for our threshold heuristic, what we are seeing and we are seeing the solutions over here in the picture, what has happened here is that all of the gray lines, they are lines that have a high power risk. And then all of the lines that have a high wildfire risk, and all of the lines that are green have a lower wildfire risk, so they are below that threshold. And so essentially for this threshold heuristic, we are shutting off only based on the threshold. So if a line is below that threshold, we keep it in service. If it is above, we shut it off. So this is a prioritization only based on risk. Now, if we compare that with our optimized power shutoff, we see kind of a quite different picture. So here you can see that all of these little triangles, gray triangles here, they correspond to the inactive lines that have been shut off. All of the blue dots here, green dots here, they correspond to the lines that are still in service. And you can see here that in this picture, there is not a clear shutoff. Before, we were just saying okay, if it's below 20, we will keep it in operation. If it's above 20, we will shut it off. Here, there is no such clear cutoff. Instead, we see that many lines that have a high risk, they are getting shut off. But there are a couple of lines that have a high risk, but they also have a very high power transfer, which indicates that they are important in order to serve a lot of load. And so some of those high risk, but high power transfer lines are actually still being kept in operation by our optimized power shutoff problem, because we are prioritizing not only based on risk, but also based on the power transfer and the amount of load that we are able to serve. Conversely, we also see that there's a lot of lines here that are relatively low in risk, but non-zero, and they have been shut off because they weren't so important in order to serve the load. So this just highlights that, but taking this more comprehensive view, where we are looking at both risk and the amount of load that we are able to serve, we are able to get better solutions. Okay, so one question that you could ask me is, here I'm looking at a relatively small system, and you know that this is this mixed integer linear program. Mixed integer programs tend to not scale very well, and so you can ask me, does this scale? And so in order to check that, what we did was that we took several other kind of standard IEEE case or just standard test cases, and ranging in size from the 57 bus test case to a 500 bus test case. So these are all taken from the PGLib OPF test cases. And for these systems, we randomly assigned risk values. So sort of based on the values that we had for our previous system, we just attached them to different components, and then we solved the optimal power shutoff problem. And we did this because we are randomly assigning those risk values. We did this for 20 different replications. And so what you can see here is that for most of these systems, these problems, they solved within a few seconds. So even in particular, for this 500 bus test case, we are only seeing the largest solution time that we saw was only 6 seconds. So this kind of indicates, and particularly some of these very, very fast solution times here, indicates that our problem is such that when we're trying to solve the mixed integer linear problem, the continuous relaxation of that problem might be tight, meaning that we're able to, we don't have to go very far down in our branch and bound tree in order to find the optimal solution. There are some outliers here. We are solving, of course, a mixed integer linear program. Mixed integer programs can have, they can have exponential complexity in general. So there are some cases here which have a really, really long solution times. And in particular, this 89 Pegasus case, that just seems to have been a really hard case for these solvers to find a good solution for. So does it scale? There are indications that it would, but for some systems it's harder to prove optimality, and it will take more time. Okay, so that brings me sort of to the conclusions for this first part of the talk. So essentially, what we are presenting here is essentially the first method that we could find that had been looking explicitly at optimizing public safety power shutoffs. The important part here is that we are actually making decisions about which components to turn off before there is any wildfire ignition. And the reason we are considering this case about being proactive about turning off the lines is because if you don't turn off the lines, once you have a wildfire ignition, that wildfire can become really large and really troubling to handle and can cause a lot of damage and also loss of life. So that's why we are looking at here, this proactive case of turning off lines even before there is any outage. So what we also saw is that we believe that this performs consistently better than what appears to be the current industry practice. So we're hoping so that is better than just taking lines out based on the risk thresholds. And then the reason why this is working better is because our optimization problem does opt to keep some high risk lines in operation in order to keep the lights on for more customers. It's also interesting to note here that this method, although it is a mixed integer program, scales surprisingly well. Okay, so that concludes my first part here. But then I also wanted to talk to you a little bit about system restoration. So this is going to be a little quicker here. Because once we have turned off these lines, we of course also want to bring them back on again. And this case of restoration is a little special because different from a situation like where you have a hurricane or other big storms that come through, the operators actually know which lines they have turned off here. They were the ones who turned them off, so now they also have to turn them back on again. But before you're able to turn a power line back on again, after you've started the public safety power shutoff, you actually have to go and check it and inspect it just to make sure that you don't have any wind damage on that line, that if you connect that line again without inspecting, you could cause an ignition and start a fire. So essentially here, what I will talk about next is some work. This is also based on work with collaborators at Los Alamos National Lab, which is looking at different algorithms for network restoration in situations where you have a very large number of damaged components. Okay, so just first, what is the goal of system restoration? So our goal here is to find the best restoration sequence, which maximizes the amount of electricity served over time. So we can think about it as sort of the graph over here. In our first time step, we have a relatively high electricity that is not served. Then in the next time step, we are hoping that we are able to repair some components that reduces that amount of electricity not served. And then so on and so forth. As we go over time, we are able to decrease that amount of electricity not served. So our goal here is to essentially minimize the amount of electricity, the integral over time for how much electricity we are not able to serve. So we are looking at a couple of different, so the main goal of this work is to find out how can we find those optimal restoration sequences in a fast manner that gives us good solutions, because solving this problem is actually really, really hard. And so that's what I'm going to talk about next here, is our work on finding those scalable restoration algorithms. So first, let's take a step back and talk a little bit about why restoration problems are hard. So if I have a system that has a very large number of components and I have to order them and decide which one I'm going to do first and which one I'm going to do next, it turns out that I have to think about essentially a number of time periods, which is equal to the number of components that need repair. And so you can think about, I have a first component where first time step where everything is damaged, then I'm going to repair one component and one more, and so on until I have repaired all of my components. Now, in each time step here, we are solving a mixed integer optimization problem, which to determine which of the components is it that I should repair. And then in addition, all of those time steps are coupled, because sometimes I have to think about not only what can I repair in this time step, but also what can I repair in the next time step in order to get an optimal solution. And this is something that has been shown, is that if you are just doing this greedily and thinking about it time step by time step, you are likely not going to get as good of a solution as if you are optimizing the whole process at once. And so this is a really challenging problem, because now we have all of these time steps, which are each a mixed integer optimization problem, and you have to consider them all at once. And then in particular, inside each of these, so there are different ways in which we can think about making this problem more tractable, because inside each of these boxes, we also have full power flow problem that we have to solve. And so the first option that we can play with here in order to make this more tractable is that we can work with different kinds of power flow formulations. So for example, I can use a DC power flow, second order cone, convex relaxation, or an AC power flow. And essentially, as I'm going down this list, I'm increasing the accuracy of my model, but I'm also increasing the complexity. The second option I can do is that I can try and come up with some good heuristics in order to reduce the number of time steps that I have to consider at the same time. So we are first just going to talk about this option 1, and then we're going to go to option 2 after. So here is just sort of to put it up there. This is the AC restoration ordering problem. So here we're trying to, as I said, maximize load serve subject to power flow constraints. We are assuming that we have to have a set of power flow constraints for each time step. We have power flow limits and angle difference constraints. We have voltage constraints. And I will also just add here that we are allowing some voltage violations in these cases, which are penalized in the objective. And that is in order to avoid AC infeasibility for buses that are not yet repaired. So there is certain, actually formulating just an AC power flow problem or an AC optimal power flow problem and guarantee that that will be feasible, even if you have thrown a lot of damage into your system, even that in itself can be hard. And so we also have generation constraints, and then we have restrictions here on the number of repairs that we are able to do per time step. And so here we will be assuming that we cannot do more than one repair per time step, but it is possible to wait to energize components. So I could say, I'm not going to energize, I'm going to repair a component this time, but I'm not going to energize it. And therefore I'm going to wait, in 2 time steps from now, there's going to be 2 components that come online. So that's the full problem. So this is the problem we would like to solve, but this problem is really hard for the reasons that I was just saying. And so essentially, like what I can do here is that I can play with what is this, how do I formulate those power flow constraints? Here I'm using the full AC power flow constraints, which are non-convex, non-linear, and combining those with mixed with integer variables means that I am trying to solve a mixed integer nonlinear program, which is approximately as hard as it gets when it comes to optimization problems. Okay, so if I'm trying to do this, as I said, there's a restoration ordering problem. And so the first thing I can do is I can try and solve it using this full AC power flow representation, which has the benefit that it will give me an accurate solution. However, it is also extremely computationally heavy, and it's easy to get stuck in local optima or in local infeasibility when I'm looking for a solution. That's what we found in our simulations, at least. I could also use an SOC, convex relaxation. This has the benefit that it is convex, which means that I can go for global solutions. I also have access to much better optimization solvers for this type of optimization problems. There are better algorithms available. However, of course, there is a problem that the solution that I come up with might not satisfy the AC power flow equations. And then I can also use a DC power flow, which is a linear representation and does much faster than either of the two other ones. But of course, this is just an approximation. And in addition, I'm not able to account for reactive power, which can be very important when we're thinking about restoration. So these are kind of like, okay, so this is hard, right? I mean, now I have to choose one of these power flow formulations, and one of them, I mean, some of them is more accurate, but more computationally heavy. Others are fast, but they are not very good necessarily. And that means that the restoration solution that I come up with, if I use, for example, DC power flow, might not be AC feasible. However, it turns out that what I can do is that I can solve this problem and I can come up with a restoration sequence. And I can then take that restoration sequence and I can pass it into a separate problem which we call the AC redispatch problem. And so in this AC redispatch problem, I have fixed the sequence of repairs. And now I'm just looking at the individual time steps. And so I'm trying to optimize the AC. I'm solving essentially an AC optimal power flow for each of the time steps without any integer variables. And this means that even if I used a DC power flow in this first step, I am able to actually find a solution over here, which is going to give me an AC feasible generation redispatch. And it is also going to tell me what the true load shed of my solution is going to be. What is the best possible load shed that I can hope for if I use this restoration sequence that I came up with here. So essentially, by decoupling the restoration ordering problem and this AC redispatch problem, I'm able to I can get away with maybe solving a simpler problem over here, but then solving this continuous optimization problem later. So the other thing that I can try and do if I want to make this simpler for myself to solve here, so we're talking about the different kind of power flow formulations. The other thing that I can use some heuristics to try and reduce the number of time steps that I'm considering at the same time. And so here, the key idea that we have been looking at is that it might be possible to identify a small number of components that are most important for serving load, and then we can just try and identify the order in which we should repair those components first. And so essentially, so we then split it again up into two steps. So the first step is that we are identifying the most important components. So here we solve again an optimization problem, which is called the minimum set restoration problem. And this is essentially a problem that is trying to identify the minimum set of components that we have to restore in order to serve the full load. And this is only a single time step problem. There is not multiple time steps. I just look at one single time shot, and then I'm trying to identify which components do I have to repair. And again, here I could do the same thing. I can solve this problem using AC power flow, SOC, convex relaxation, or a DC power flow. And what I get out from this problem is that I can see that there are what are the set of components that need to be restored in order to serve the full load. And so once I have that set, I can take that smaller set of components, which means that I have fewer time steps that I have to consider in my restoration ordering problem, and I can solve this problem with those fewer components. And again, here, I could use either an AC power flow, an SOC, or a DC power flow formulation. And then I come up with a new restoration sequence. And of course, I can also take this one and now go back and do an AC redispatch as well. So I can combine these things in different ways. So that's essentially what, just as some examples of how we can combine it. So one version of this would be to just solve the AC restoration ordering problem, which has the benefit that it will give an AC feasible solution at once. You don't have to do that kind of pre-processing of solving the AC redispatch. However, at least in our experience, this is pretty computationally intractable once you get to a larger number of damaged components. You could also combine this restoration ordering problem, for example, solve an SOC or a DC ROP problem followed by this AC redispatch. This would give us an AC feasible redispatch solution. It might also be much more computationally tractable because we're solving a simpler problem here in the middle, but it might not give us an optimal solution, right? We don't know, because it could be that the SOC or the DC ROP is overestimating the amount of load that they are able to serve, because it's a relaxation and an approximation, respectively. And then finally, we can also just combine this in all different kinds of ways. So for example, one way of doing this would be that I solve a minimum set restoration problem where I'm using the second order cone problem in order to determine which components do I have to restore in order to serve the full load. I can take those components, I can solve those using the DC ROP, and then I can use an AC redispatch in the end in order to get the restoration solution. So, there's many different ways in which we can combine this, but it's interesting here to understand what are the best ways. So essentially, what combinations of these steps is it that gives us good solutions that are getting us a solution fast and also give us a solution that is close to optimal, meaning that it's minimizing the amount of load that we're not able to serve. And so I'm just going to take us briefly through some results here before we will open for questions. But so here we are going to talk a little bit. Let's first just look at some results here for the 5-bus system. So this is a very small system. We're looking at this very small system because we are able to solve this ACRP problem for this very small system. So first, for this small system, we are going to assume that the whole thing was damaged, everything was out of service, and now we are restoring components one by one. And you can see here, on the y-axis here again, this is the energy not served, and this is the restoration period here at the x-axis. So you can see here, these are the solutions for the DCROP, and also some statistics listed over here. You can see that this DCROP, it solves very fast, and it serves the whole load after 7 time periods. And I should say here that this DCROP solution is after the AC redispatch. So this is after, so the DCROP thought that it was only going to lose 2,900 megawatt hours of load, but the true expected load not served here is actually 2,902 megawatt hours. But that is pretty close, right? This is well within 1%. So the DCROP is performing really well here, and we also get this solution in 12 seconds. Now, if I add on here and I look at the SOC ROP, I can see that the SOC ROP actually finds the same restoration solution as the DC ROP, so the same ordering. And we can also see that the SOC solution has a very similar, I mean, it is underestimating this, the energy not served a little bit relative to what is true, but this is very close again. And so we can essentially say, because the SOC is a convex relaxation, we can claim that this is probably the globally optimal solution for our restoration of the system. Now, we can also look at the ACRP. And we know that this is the most kind of accurate model for this system. However, what we are observing here is that this problem takes enormously long to solve, much longer, 900 seconds versus 2 seconds for the SOC and less than a second for the DC. And we can also see that it actually finds a solution that is worse. So the ACRP sheds about 1/3 more load than the other 2 problems. And you can see it also on here that in many time steps, the amount of load that is shed with the ACRP solution is much higher than the others. And so essentially, it's not only slow, but it also finds a local maximum, a local minimum here. And so this can be a problem. Yeah. So we could also, as I said, we can use this MRSP problem, the minimum restoration set problem, to identify the smallest set of components to repair. And so here we are just comparing the solutions that we obtained with the SOC power flow formulation and the MRSP as a preprocessor versus where we are solving it directly with the ROP. And what you can see here is that with the SOC MRSP, we are able to restore the full load faster after 6 times that. However, it turns out that the SOC ROP chooses here to wait a little longer to restore the full load, but therefore is able to restore more of the load already in time step 6. So you can see that in this case, when we are doing this minimum restoration set problem as a preprocessor, it is only a heuristic. And then finally, I should also say, like, we also, of course, want this to go beyond a 5-bus system. It is still, I think, here an issue of tractability. We were looking at the IEEE 118-bus system, where we have 35% of all lines and generators that are damaged in one part of the system, in one area of the system. And here we find that the DCROP solves it in 6.8 seconds. So we are able to get a very fast solution. And that is this blue solution. But you can see that if we take that solution and we pass it through our AC redispatch algorithm, then we observe that the AC redispatch predicts that we are going to lose more load than what the DCROP thought. So essentially, the DCROP is a little optimistic here. And so, finding ways of formulating fast problems that don't have as much of a difference between the solution that is proposed and the true AC redispatch, that can be important. Yeah, so that's sort of what we are looking for. So our conclusions here is that the AC restoration ordering problem is quite intractable and has a tendency to get stuck in local solutions. The SOC formulation can provide a globally optimal solution. Unfortunately, if you're looking at larger system, it is still pretty slow. A DC ROP is faster, but it does fail to consider reactive power, and that is actually a very important component of restoration, so that is a problem. Meaning that we don't get as good solutions there. So that means that there's still a lot of open questions. Tractability here is still a challenge. And the goals that we are working towards is really to find some fast and reliable algorithms for restoration. And that includes both looking into heuristic methods to determine fast restoration sequences, but also to kind of pull different kinds of integer programming tricks in order to try and make these algorithms just run faster. Okay, so with that, I just wanted to put a little plug for our code here. So we are releasing a lot of our code online. Power Models Restoration is a package that was developed in collaboration with Los Alamos National Lab. So it's part of the Power Models packages in Julia. So if you are not aware of those, I recommend checking them out. The Wildfire work, you can also find code for that on our lab webpage on GitHub, Power Models Wildfire. There we are also, if you happen to work with Power Models as a package, we have also developed plotting algorithms for plotting to make it easier to look at the results that you are getting from Power Models and make plots such as the one that you are seeing here. So if that is something that is of interest, I just want to put in a plug for that here. And I think that's it. Thank you very much.
Thank you. I think that was a very interesting talk. And as you can imagine, there are more than 20 questions.
Oh, wow. OK. Sorry. Yeah. And I guess I maybe went a little over time here. Sorry about that. So, yeah.
Yeah. So the first one is that, how these things will change when you have a renewable energy transition.
So how the things will change in terms of the wildfire?
Yeah, all the optimization and the resources are also towards the edge, and,
Right. So yeah, so I think that if I go back and I just pull up my slide here on the we had this one here where we were looking at optimizing this wildfire. Here you are really seeing also that there's benefits of distributed generation. So having more distributed generation, you can clearly see the benefits of that. I mean, this wasn't something we explicitly modeled for, but it's an interesting observation. And of course, the availability of that generation is also going to change when you have more renewable energy. So maybe sometimes you will then end up shedding more loads. And so that is one of the things that we are looking into here is getting better models for the wildfire risk, but also understanding better how different kinds of, how does the risk of wildfire coincide with availability of, for example, renewable energy in the grid.
Mhm. Well, next question is that how a rapid outage causal diagnosis will help in this case. Of course, wildfire is one reason, but there will be other reasons that things will be failing. So if you can detect and diagnosis all those causal for basically cause for all the different things happening, how it will help and fit into this solution.
Yeah. So I think that, so there is certain things. So in context of the wildfire ignition, there are certain things we know about if you are able to interrupt the fault current faster, for example, then or you are able to have, these kind of predictive devices that are able to sort of say, hey, there's a high risk that we are going to see an outage on a specific power line ahead of time, then you can also take action based on such information from sensors. So that can be really useful. The real big challenge with wildfire ignitions in particular is that once you have an ignition, you might already be lost. Sometimes the conditions are so windy that if you get a wildfire ignition, there is nothing, the firefighting isn't helpful. You can't do anything. You just have to let it burn for a while. You can't directly attack the fire because it's just growing too fast and it's getting too intense. So that is sort of some part of this. Of course, then in the context of the restoration, when you're doing restoration, it's very important to know what components that are outage and which you need to restore. And so kind of having a better idea of that, and in particular in a situation which is, other situations than wildfire, I think that is absolutely super important. Because the sooner you can establish which components you need to repair, then the sooner you can get them back online again, right?
So it will be okay to go like 5 more minutes.
Yeah, I am available.
So the next thing is that it seems like the fire risk model is based on historical data, and especially, I think there's not a good answer to this question, but it says, for example, in Washington State this year, there were wildfire in areas that had never burned before and were considered low risk. So, of course, how do we consider these? Yeah.
Yeah, so that is a very, very good question. And that is why we are looking, just coming back to this, right? We know that unfortunately, and yes, Washington State is definitely pretty red on this map, right? So when you assess, so in our model, we were using wildfire risk that is based on historical data, mostly because we were, this is synthetic data that we were generating for our simulations to make sense. So we wanted to have some geographical correlation, and we are creating a case study. We are currently working pretty hard at trying to understand what are different models for wildfire risk. How can you model this in better ways, and also in ways that account for, various aspects of wildfire risk. There are multiple different ways in which you can measure it, including, you can measure the probability that you will have an ignition. You can measure the probability that a small fire is going to grow very large. And so kind of when you are looking at organizations who are looking at wildfire risk in particular, they are not used to thinking about risk arising from certain sources like a power grid. They are sort of generally assessing what is the risk, like how likely is it that if there is an ignition, it will become a fire. And so they are looking at things like the flammability of the of vegetation and so on and so forth. So that is kind of not directly related to the power grid, right? So in order for us, if you're going to take really disruptive measures like shutting down power lines and turning off power to people, we have to understand what the risk reduction we are able to get from that. How does that compare with the impact that it has on people? So it's important to kind of understand the marginal risk reduction that you get from shutting down a power line. And so we are working pretty hard on trying to understand that better. One thing I wanted to say, so coming back to the question about historical data, is that while we were using historical data, assessing wildfire risk is not based on historical data. You can wildfire risk, for example, like what you are seeing here, is based on expectations about weather and like how high is the humidity in the vegetation, so how dry is it, how has there been any rain recently, and questions like how high is the wind, and so these kind of weather patterns is what you would in an actual scenario, if you're going to use the methods that we are using, you would get that kind of real-time data and assess the risk based on that. And of course, in Washington State, there has been increased wildfire risk already this year. This is happening, and you will be able to kind of take these kind of risk assessment methods and evaluate the risk also sort of based on current condition, not only based on historical conditions.
Mm-hmm. Yeah, so there are several other questions, but I will get to the starter one you can answer. So the next one is, did you consider the presence of normally open switches?
Yeah, so in this case, so what we were looking at here, we were mostly considering, we have been considering sort of this from a transmission system perspective. So here for the wildfire, but also for the restoration, I will say. So that was partially based on the collaboration that we had with Los Alamos, who's also has been looking at and developing also tools for what is called the severe contingency solver, which is sort of a setting where we are looking at a hurricane coming in over land and damaging the transmission system also. So our main focus so far has been on transmission rather than distribution.
Mm-hmm. Okay. And then there's another question about, I know that you have a different problem set in case studies, but what was the maximum integer variables that were considered and what solver was used? I think maybe it's in your open source code or?
Yeah, so definitely, and I would be happy to answer questions about this, and I can also help connect you with my student who is working on this. If you have questions about this, as I said, there's a GitHub repository if anyone is interested in just checking it out. So the thing one thing I can say about this is that I was showing some results for scalability here. In this case, in the case of the wildfire risk problem, here we have integer variables for every bus, every line, and every generator, and then we have continuous variables for loads. So there's a pretty large number of integer variables, and it turns out that the number of integer variables is not the main complication here, but rather there's something else going on. We believe this has to do with the objective that we are using, which is just trying to minimize risk, meaning that we have the integer variables, they are appearing directly in the objective function, and that kind of is something that can help you find solutions faster. Yeah, maybe one more thing to say about that. The solvers that we are using is for the DC and the SOC case, we are using Gurobi, which is able to handle these cases. For the AC one, we have been using Juniper, which is a mixed integer nonlinear solver developed by Los Alamos.
Okay. And given that risk areas are typically going to be same, is that possible that optimized shutoff will repeatedly impact the same areas over time, and maybe those are rural areas?
Right. Yeah, I think that is a really important and important question, right? I mean, where is this going to be the same people seeing power outages all the time? And I guess the question to that is that yes, I mean, if the wildfire risk patterns, which are often tied to types of vegetation, topology, and areas with a lot of wind, they tend to repeat. And appear in the same places. And oftentimes it does have to do with lines that go through long stretches of wooded areas. they might be the riskiest ones. So yeah, it might be that the same lines are being turned off over and over again, and that's where, you know, having distributed generation, the ability to kind of create microgrids along the way to serve load more locally, all of these are very important things to consider in order to mitigate the impact on communities that might see many power outages.
The next question is that how does this algorithm map to a distribution system, and you know, where you can feed the power in typically one direction unless there is a DR. And also the third one is that in that set of variables, other than line shutoff, did you also consider disabling recloser, right? I mean, that typically we consider in distribution system.
Right. Yeah, these are excellent questions. So we have not specifically considered distribution systems. It's something definitely that is on our mind. And I heard someone told me that this is also work that is going on in this group as well. So I'm looking forward to check that out more. So you know, we are thinking about distribution systems, and we just want to make sure that we get the modeling of this right. There's nothing here that kind of would prevent us from taking this method and sort of applying it directly to a single phase equivalent of a distribution network. But of course, we also need to think more about, like, how do you maintain radiality and all of that. For the reclosers, we haven't explicitly included that here yet. Also, again, something we are thinking about. Part of the reason for that is that when you are modeling the impact of turning off a recloser, you have to also model what happens after you have a fault. And so kind of the modeling that is going into that then becomes sort of more of a multi-stage problem. And so that is definitely something that we are also working towards understanding this better. So where we are considering how multiple kinds of action could supplement each other. Yeah, and similarly also here we are not considering anything like N-1 security, right? Which kind of goes to a little bit of a similar question. You know, how long would an outage be if an outage happens after you have turned off a line? Because it might be that you have an outage, but you don't have a fire, and then you still want to be able to model what that outage means in terms of serving the load. So definitely very great questions.
So I think I mean, there are several more questions, but I'll ask one more, which is more like a comment. Is, you know, with limited crew, repair crew, when we do the sequence of repair, we should also consider that, you know, how far crew can go and how many crew members have access to reach a different location. And then, of course, it will make it a little bit more complex restoration problem, you know, with the crew.
Yes, definitely. I agree. We are, I guess, one way of thinking about what we are doing here is that we are solving a simple problem in order to understand the algorithmic aspects of it, in the hope that what we learn from that can help us also formulate and provide, you know, better solution algorithms and insights into how we can solve these other more complex and more realistic versions of the restoration problems faster.
Mm-hmm. All right, thank you so much. I think we're several minutes running late, and that's good. That good problem to have, that you have more questions.
Yeah. No, thank you so much. I mean, if anyone, I mean, if there are people, and I mean, students or anyone on the call who wants to have more questions to ask, I mean, I would be happy to stay on another 15 minutes or so to just chat with the students, if that is something you do. But otherwise, I will just say thank you for the invitation. It's been great to be here.
Sure, yeah. I mean, what I'll do is that I'll copy some of these questions and send you. So, you know,
Perfect.
You can put a reply later.
Definitely. And again, also, I'll just put my email address also here. Yeah. So if anyone wants to send me an email and have questions and follow up, you know, it's I would love to hear from you. So yeah.
Hi, thanks so much.
Yeah, thank you so much.
Bye.